So now that we've defined our magnetization and considered the vector potential coming from a certain chunk of matter with this magnetization, we can look a little bit further into the original equations that we had written for the magnetic field and try to see if we can rewrite them. I remind you of the logic back then. The idea was that there were like global equations and local equations. So you've got an equation now for the vector potential in terms of an integral of either the magnetization throughout the bulk or of the bound currents and bound surface currents. But we like equations which are local. We like things that are essentially defined in a certain point in space. And you remember what we did in electrostatics. We transformed these integral equations that we had for the potential into local equations like the Poisson equation. So in the case of the magnetic field, we've discussed Ampere's law. You remember Ampere's law just tells us that the curl of B is equal to mu0 J. Now, similarly to what we did in the electrostatic case, once again, in the presence of matter, we will decompose the sources of our fields into different pieces. Here, we will decompose the current into both a bound current coming from the magnetization inside the material that we've just seen, and a free current. The free current being really what you can add to your system externally, what you actually control, what you just plug in when you do the experiment. Okay, but not stuff which is bound to the chunks of matters that you're considering. So given this decomposition, which exactly parallels the decomposition that we did in the electrostatic case between the charge density and the bound and free charge densities, now that we've got this decomposition, we can reconsider Ampere's law and rewrite the right-hand side of Ampere's law as the sum of these two contributions for the current. But the bound current, of course, is just given by this curl of the magnetization, like we've discussed just previously. So this suggests a convenient rewriting where we only use the free current as a source of our equation, and we just push this curl of M to the left-hand side of the equation. So that's simply done by defining a new field. H doesn't carry a much more original name than H. So we define this H field as a particular combination between the rescaled magnetic field and this magnetization. And the point is that this H field obeys a form of Ampere's law, which has only the free current as source. So curl of H is equal to the free current. And of course, because of Stokes' theorem, you can write also an integral form of this equation here, just by taking the integral of this over a certain surface, bounded by a certain path P. Then you end up that the path integral around a closed loop of H has to be equal to the total free enclosed current. All right, so this object here is just the integral over your surface of the normal vector dotted into the J-free current. So that's the definition of the H field itself. In the presence of matter, it's usually much more convenient to compute the H field rather than the magnetic field, because the H field hides the complexity within itself of the magnetization of your material, right? So as a very simple example of this, we can consider the following problem. So we have a cylindrical rod made of some magnetic material. It can be copper, it can be anything else. Copper is quite common. So we imagine that the cylinder is infinitely long. Therefore, the magnetic field in that does not depend on the position along the axis of the cylinder. For definiteness, we put the radius of the cylinder to be this r, and by just symmetry, we expect the magnetic field to be circumferential. So it would go along the phi hat direction if we use cylindrical coordinates around the axis of the cylinder. So the question is, just find this vector field H. So like we've said, H must have the form that it's circumferential, and of course its value will depend on the radius at which you evaluate it. So how do you compute this? Well, we will use Ampere's law here for H in the integral form that we've just seen. And what path are we going to use? Well, we're going to center a circle of radius r on the axis of the cylinder like this. So let's just compute the left-hand side and right-hand side of this. The left-hand side uses the fact that, so dl is just along the phi hat direction. H is along the phi hat, so the dot product just becomes 1, and then you just integrate over the whole circle thing, which is then constant. So you just get 2 pi r times the value of h at that particular radius r. So that's the left-hand side of the equation. The right-hand side of the equation is the total free and closed current. Now, what we suppose is that the rod carries a total current I, which is uniformly distributed throughout the area. So if you want, the flow of charge is uniform, irrespective of where you're sitting on the cross-section of the cylinder here. That means that if I look at a certain loop at radius r, the total free and closed current, if r is greater than the radius of the cylinder, then of course it's the total current I. But if my r is within, so if I imagine having a little circle of a little radius r smaller than the big R radius here, then I would find a current which is proportional to the surface area of that little section here. So that's why I've just got this extra factor here. If r is less than the radius of the cylinder, I just need to correct this by some r squared over radius squared here. Okay? So equating left-hand side and right-hand side immediately gives us the answer for the H field of this configuration. It's got a different value inside and outside the cylinder. Okay, so it grows with R, reaches its maximal value at the radius corresponding to the radius of the cylinder, and then starts falling like 1 over radial distance. Now, similarly to the electrostatic case, although we have H, we do not have enough information in our possession to compute the actual magnetic field inside the cylinder. Outside the cylinder, of course, the magnetization vanishes. And in that case, there's a direct equality, there's a direct proportionality between H and B. So outside the cylinder, the actual magnetic field is given by the usual expression that we've seen a few times of a current carrying wire. Okay, so it's exactly the same irrespective of the radius of the actual cylinder carrying the current. The only thing that matters is the size of the current that we have here. If we wanted to know the magnetic field inside the chunk of matter, we would need to know more information about the relationship between the magnetization and the applied magnetic field. Okay, so that's something that we need to characterize for each particular piece of matter that we're considering. Okay, but as far as the field H is concerned, we can just legitimately use all these tricks that we've seen before with Ampere's law.